Okay, ladies and gentlemen, good. Let's see if the audio is on. Good morning to all of you on this cold morning. I don't know. Let's talk about a couple of pictures here. Okay, you got two pictures to talk about. If we draw it this way, here's the y-axis. Here's your x-axis. And I'm going to draw a picture that looks like this, okay? This is what we call concave what? Down. And then this is what we call, I'm going to change the picture on you. Got to do a little smoother. Okay. This is what we call concave up. And then we're going to express to you guys why here. Okay. Okay, why is this called concave up, concave down? I want you guys to know a couple of things here. Think about rain and whether or not these shapes hold water. Over here on the right, if it rains, the one on the right, being concave up, holds all the water. Is that true? It looks like a cup. And then one on the left, concave down, does not what? Does not hold water. I just want to kind of describe the picture for you guys. Okay, just to describe these pictures. Now, give you some definitions here. If the graph of f lies above all its tangent lines, okay, on an interval I, then we say the graph is concave up. All right, so I'm going to share with you guys where that is. I'm going to draw the picture. So if the graph, this is the definition of being concave up. And concave up, ladies and gentlemen, I'll just put CU. I abbreviate that CU for concave up. Now, here's what that means. You got all these points on the curve. And if you notice, on this curve, you have a horizontal tangent line. Is that right? But to the left, you have another tangent line, and then you have another tangent line here. So you have all these tangent lines. Try to get that last one in. Okay? Those are our tangent lines. All these tangent lines are below the curve. Is that right? So we say this curve is concave up on that interval. Comparing that definition to being concave down, right? Here's the definition of concave down. If the graph of f lies below all its tangent lines on an interval I, then we say the graph is concave down. Okay, CD for concave down. And here's kind of what that means, and here's what that looks like again, right? You got all these points on this curve. And then, for example, here you got that horizontal tangent line. Okay? And over here, another tangent line. Another tangent line. So you got these pictures of these tangent lines. All of these tangent lines are above the curve. So when that happens, when f lies below, the function, the curve, is all below those tangent lines, then we say the graph is concave down, okay? So this is the definition of being concave up, concave down here. All right, you guys okay with that? Easy peasy lemon squeezy? Remember, holding water and then what? Not holding water. I don't know, maybe we'll change colors here, right? Concave up is orange. Concave down will be green. Hold water, not holding water. This is called concavity, ladies and gentlemen. Now I'm going to give you guys a couple of facts, okay? Here's a fact. This is what we're really interested in today. Okay? If I take a look at this situation, if I look at the derivative of the first derivative and it's positive, remember, here's what I'm saying to you guys. This first derivative is called m tangent. Right? At a location x. Isn't that your slope of your tangent line? So here's what they're saying. By that first derivative being positive, then what they're saying is those slopes are increasing. Those m tangents are what? Increasing. All right, so where is the m tangents increasing? Well, over here. Okay? They're talking about the slope of all these tangent lines. So if I'm walking left to right, what you're going to notice is all of these here, slopes of those tangent lines, are actually getting bigger. They're increasing as you go left to right. So what they're saying is, in other words, if your second derivative is positive, that's where the curve is what? If that second derivative is greater than or equal to 0 on an interval I, then your curve f is concave up. Okay? So I want you guys to know that the second derivative being positive means that curve is concave up. And then similarly, the other fact, written this way, if we look at the derivative now of that first derivative and we say it's less than 0, remember this is where all the what is? M tangents. If the slopes of the tangent lines are what? Negative. Decreasing. Going left to right, left to right. Notice this. All of these slopes are getting what? Smaller. Because that's this. This is m. We're saying m tangent is decreasing. So if your first derivative is decreasing, that's what we're saying. That first derivative, the derivative of the first derivative is second derivative. If that is negative on an interval I, then f is concave down. Okay, so I just want you guys to know those two ideas here. And that's what we're going to be looking at here today is concavity. Where is it concave up? Where is it concave down? Your curve. And I got to give you one last definition. Okay. Definition right here. Definition. The point xy on a curve where concavity changes. You say, what does that mean? Concave up to concave down. Or concave down to concave up. The point where it changes is called an inflection point. Okay. Whew. So you can have inflection points, the points where you change concavity. All righty, ladies and gentlemen. So now you might say, Mr. Judge, should we do some examples on this? Sure. And here's what this is all code for. This is all code for, ladies and gentlemen, sine analysis on what? Your second derivative. So I hope you guys have been working on your sine analysis skills because you're going to use that again, but this time it's going to be on the what? Second derivative, okay? You guys okay with that? So let me go back now and try to look at what we've done for intervals of increasing, decreasing. Right? So we can do all this one here. Let me see here. Yeah, let's try this one. Okay, is that the first one we did? No, there's actually, here's the first one we did. Ooh. Should we try this curve? I think, is that, and if I go back, I'm just kind of curious. Let me go back to my website here. Because I got some options here, I think. And that's the problem. You have so many options. So many examples to do. If I go back and look, what do we do here? Here's the interval of concavity worksheet. Right, you see all these here? I even did what? On the video, you guys have these examples. So I have these examples already for you. So I don't know. I mean, you could look at those examples, but I might want to look at what we have so far. Let's look at this one, I guess. Let's look at the first example we did, right? See that curve? Let me do the following here. I'm going to copy that. And let me also copy the first derivative. You guys remember that? First derivative on intervals of increasing, decreasing. Okay. Okay, so we did sign analysis on that first derivative now. So now we're going to look at the intervals, intervals of concavity now. What does that mean you're going to have to do? Right? They're going to say your intervals of concavity. You're going to need that second derivative on sign analysis. So the second derivative will be now the derivative of the what? First derivative. And your first derivative is a quotient. Is that true? All right, so we're going to have to get the second derivative now. And so remember what we do. You take the denominator and square it. You bring up the denominator, differentiate the numerator, minus the numerator. You differentiate the denominator. Okay, so let's double check here. Let's get some derivatives here, right? So this is going to be negative 2x. Is that right? This one, though, is 2. X squared plus 4. Don't forget by chain rule, that's 2x. Is that right? Okay, so don't forget chain rule here. So I'm going to write all of this down here. That's going to be negative 2x, x squared plus 4 squared, minus let's be careful here. Minus what? 2 is that 4x x squared plus 4 times 4 minus x squared over x squared plus 4 to the 4th power. All right, you guys okay with that? Double check to see if I did this correct. 2, 4x. Okay. Now I'm going to factor out the greatest common factor here. Okay, so I want to factor some things out. Now let me get some highlighters out here. Right, we're going to do this term by term. So the greatest common factor is going to be, I'm going to take out the negative 2x x squared plus 4. This is to the 1th power. Always take out the smallest power. It looks like what you have left is a x squared plus 4 plus 2 times 4 minus x squared over x squared plus 4 to the 4th power. Let me double check. Okay, it looks okay. So I still have that negative 2x. X squared plus 4 now. I'm gonna do some algebra here. I'm gonna simplify here. That's plus 8 minus 2x squared. I think that's 12 now. 8 plus 4 is 12 minus x squared. Double check. Okay, now you have x squared plus 4 to the 4th power. Second derivative, what do they call that? F double prime? Okay. So double check my algebra this morning, ladies and gentlemen. I haven't had my second cup of coffee. So double check that. This is your second derivative here. Okay, now remember, what are you supposed to do with this second derivative? You have to do what? Sign analysis. Remember, what's the domain of that original function anyway? Go back to the domain. This domain is all what? All real numbers. Is that true? Because your denominator here will never be 0. X squared plus 4 can never be 0. So it's all real numbers. And so again, by doing sign analysis, you want to set that numerator equal to 0 and that denominator equal to 0 because you have a rational function. So if you said that second derivative will be 0 where the 2x, x squared plus 4, 12 minus x squared will be 0, that is true. And then that denominator, by the way, where you want to find where that second derivative does not exist, well, that never happens. Because that denominator could never be what? 0. But the numerator sure can be 0. So you're going to solve that equation for the numerator being 0. You set this numerator equal to 0, set the denominator equal to 0. This is sign analysis. And I just want to point that out. Denominator can never be 0. I'm going to get rid of that here. Or, no, let me do this. Let me just move this. Because I'm going to do zero product rule, right? So you say, okay. Negative 2x equals 0. X squared plus 4 is 0. 12 minus x squared is 0. So this means x equals 0. This never happens. You get complex solutions. And then this means x squared is 12, which means x is plus or minus square root of 12, or x is plus or minus 2 square root of 3. So here's my solutions. Never what? Happens. Okay. So sign analysis. Let's get out our regions here. So now, let's see what's going on here with this. Negative 2 square root of 3. 0, positive 2 square root of 3. Second derivative. This is where your second derivatives are zeros. Region 1, Region 2, Region 3, Region 4. You guys need some test points. Okay, so what's the value of like negative 2 square root of 3? Do you guys know? I don't know. What's the square root of 3? Do you guys remember? You said, I don't know. Well, what's negative 2 square root of 3? It's about negative 3 point something. Okay, because the square root of 3 is about what? Negative 1.7. Okay, so let's take a look here. So I think what I... Maybe negative 1, negative 4. Is that right? Positive 1, positive 4. So you got some symmetry. These are all my test points. So we're going to test every region. Okay, and that's the second derivative. Now you're going to have to test every region here. Let me see if I can bring this down here. Here's your second derivative. Now I want to point out to you guys one important idea. It does not matter what value of x you put in the denominator. If you square it, doesn't it make it positive? This is kind of a fast way of doing this. I know my denominator for all these values of x are going to be what? Always what? Positive. Remember, sign analysis, we only care about the sign. So now I'm going to plug in negative 4 for x. I really don't care about the what? The answer. I just care about the sign. You guys with me on that? So here, this is going to give me what? Positive. Negative 4 squared plus 4 is another what? Positive. And then 12 minus 4 squared, isn't that 12 minus 16? Isn't that negative? So here's all I'm saying. Positive times a negative divided by a positive will give me negative. Is that right? So region 1 is a negative region. We just care about the sign. We don't even care about the what? The answer. Okay. Negative what? Test point, negative 1. Maybe I'll keep it purple. Okay. So again, I know a negative times a negative is a positive. 1 squared plus 4 is positive. 12 minus really 1, because negative 1 squared is 1, that's positive. The denominator is positive. So, ladies and gentlemen, what do you guys notice? Region 2 is what? Is positive. You guys okay with that? Easy peasy lemon what? Squeezy. Okay, let's go back and plug in now. What are we going to plug in? Positive 1 as a test point. So I'm going to plug in 1, 1, 1. Okay. So negative 2 times 1 is negative. 1 squared plus 4 is positive. 12 minus 1 is also positive. So we get a negative times a positive divided by a positive will give me a negative answer. So region 3 is negative. Is that true? You guys okay with that? Easy peasy lemon squeezy? All right. The last test point. Plug in a 4. So let's see what these, negative 2 times 4 is negative 8. 4 squared plus 4 is positive. 12 minus 16 is negative. And we have a negative in the denominator, and positive in the denominator always. So a negative times a negative in the numerator is positive divided by another positive in the denominator. Region 4 is what? Positive, ladies and gentlemen. So this is sign analysis on the second derivative. Make sure, ladies and gentlemen, you're using that second derivative here. All right. Now, what does this mean? Do you guys know what this means? Concave down, concave up, concave down, concave up. Okay, you guys okay with that? What do you guys think? Is that okay? This is sign analysis on that second derivative. So I'm going to get rid of this, and let's look at our conclusion here. What are we going to say? F is concave down. Where is it concave down? Region 1. Is that true? Right in here. Region what? 3 right in here. So what is region 1 and region 3? Region 1, negative infinity up to negative 2 square root of 3. Union 0 up to 2 square root of 3. These are open intervals. So let me remind you guys, because some people are going to make that mistake. Why are they open intervals? Do you guys know? Why are they open intervals? At these values here, the second derivative equals 0. 0 is not positive. It's not negative. It's neutral. So it's not going to be involved in that answer in that way. Concave down is where the second derivative is strictly what? Negative. Okay, you guys okay with that? That's where it's concave down. So that's how we answer this. And then you say now, F is concave up on what interval? Well, now, region what? 2 for these values of x, region 4 for these values of x, forever. Just like over here, this also went forever, just to kind of remind you guys. Okay, so you're going to be concave up on what interval now? Negative 2 square root of 3 up to 0, union 2 square root of 3 to infinity. And that's when you're going to be concave here up. Easy peasy. Lemon what? Squeezy. Okay, you guys okay with that one? That's how you answer your questions. Now, are there any inflection points? Where are the inflection points? Do you guys remember? Yeah, the values, it's an inflection point, first of all, is a point on the curve. Has to be in the domain. It's a point on the curve. That's why they call it an inflection point. So all of these here are the x values here. This is a second derivative. Okay. So didn't you go from concave down to concave up at negative 2 square root of 3? You guys see what I'm saying? Right in here. You change concavity. So you say, what's the first inflection point? Well, it'll be negative 2 square root of 3, and then f of what? Negative 2 square root of 3. Because this is the x value. This is a y value. It has to be a point on your what? On your curve, ladies and gentlemen. It's an inflection point. That's the first one. What's the next one? Yeah, why? You went from concave up to concave down. Is that true? You go, okay, add 0. So the inflection point will be 0, really. F is 0. It's an x and y coordinate. It has to be a point on that curve here. We're looking for those inflection points. And then it has a third inflection point. You say, how do you know? You went from 0 to what? You went from concave down to concave up at positive 2 square root of 3. So these are the locations of your what? Inflection points. Yes, you would have to go back to the original curve maybe and get the y value, but this will be good enough. And, you know, if you see some of your answers in your book, they're sometimes written that way too. So, ladies and gentlemen, this is putting, you're looking at now sign analysis on the second derivative. Let's go back. What's the original curve here? Do you guys remember? X over x squared plus 4. So let's look at Desmos here. And it's not too exciting, but I have to change the, let's do this from negative what? 0.5 to maybe positive 0.5. Okay, now it looks a little bit more exciting for you guys. You guys see what I mean? So just bring it in. My old man hands. All right, so somewhere here, if we go back to the calculator, negative 3.5, positive 3.5. Let's kind of write something here. Negative, let's see, 2. Somewhere here, I think that's negative 2 square root of 3. Positive 2 square root of 3. This will be where 0 is. Okay, so let's go back to our answers here, right? What do we say about this concave down? So this is where it's concave down. And then that's your inflection point, concave up. Okay? This is what they want you to kind of see. Concave down, concave up. Does not hold water, holds water. And then here, concave down, region 3. This is where region 1 is, region 2, region 3, and then they want you to know that this goes up region 4. This is your concave up region. All right, so you guys, I want you guys to see that here as well. And yes, we did look at the increasing, decreasing as well on this. This is a prior example. So this is our first example on sign analysis on the second derivative. Okay, and you guys can see that the inflection points, again, are here, here, here. These are our inflection points. The locations on the curve where you change your what? Concavity inflection point. Okay. Just want to share that picture with you guys. You guys are looking at it right here. Okay. How about, let's take a look. Intervals of increasing, decreasing. Where is this? Part 1. We looked at this first curve. This is the increasing, decreasing part. First derivative test, relative max, relative min. Let's try this one here. Okay. And what's the domain here? Do you guys remember this domain? Dig that out of your notes. So we're going to copy that. Okay, what was the first derivative? Right here. Anybody remember the domain on this one? I think x had to be, x plus 2 was greater than or equal to 0. Is that right? Anyway, okay. So now we need that second derivative. So you're going to have to differentiate the first derivative. 2 square root 2 plus x, 3x plus 4. Okay. Quotient rule. Square the denominator. 2 square root 2 plus x times the derivative of 3x plus 4 minus 3x plus 4 derivative of 2 square root 2 plus x. So this derivative is 3. Is that right? What's this derivative going to be? Pull out the constant. Okay, let me just write it this way. Okay. So that's going to be 2 times what? 1/2. 2 plus x to the minus 1/2 times 1 by chain rule. So this will be 1 over square root of 2 plus x. Double check my arithmetic, okay? Alrighty. So it looks like I might have six square root 2 plus x minus what? 3x plus 4 over 2 over what? Square root 2 plus x over 4 times 2 plus x. Let me double check here. Okay. Now, let me do a little bit of this that I can do on my end. Going to have to do some arithmetic, some algebra. Okay. 6. 2 plus x minus, this is over square root, 2 plus x, x plus 4 square root, 2 plus x, 4, 2 plus x. Okay. How about if we do this? 6, 2 plus x minus 3x plus 4, that numerator over the square root 2 plus x divided by 4, 2 plus x. So this will now be, if we start to distribute here, 12x plus 6x minus 3x minus 4 over 4, 2 plus x, square root 2 plus x. And that's 12. That's not 12x. Okay. Is it 3x plus 8 over 4, 2 plus x, square root 2 plus x. Okay, second derivative. So what do we do with all this again? What do we got to do? Do you guys know? Yeah, we're doing sign analysis, so we have to know where that numerator is 0 and where the denominator is what? 0. Is that true? So we say 3x plus 8 equals 0, and then 4, 2 plus x, square root 2 plus x is 0. Okay. So this means x is negative 8 over 3. Is that right? This is really going to mean x is negative 2. Is that right? You guys okay with that? Double check my algebra. Is that right? So y, ladies and gentlemen, 2 plus x, you can set them both equal to 0 separately, but it's going to give you the same answer. X is negative 2. X is negative 8/3. Okay. So when I look at this sign analysis, I draw my real number line, and what I know is here's a negative 2 would be. Here was negative 8/3 would be. This is sign analysis on the second derivative. Is that right? Because negative 8/3 is like negative 2 and 2/3. So what does this actually mean? This is where my second derivative is 0, and this is where the second derivative does not exist. Undefined, I guess. This is the second derivative. Sign analysis, though, calls it undefined, but I want you guys to know this is what's going on, okay? Region 1, Region 2, Region 3. However, ladies and gentlemen, go back to your function. What do we know about this curve? What do we say your domain is? It's greater than or equal to negative 2. Is that right? Okay. So if it pays to be awake, why do I say that? Why does it pay to be awake? I don't even care about region 1, region 2. Your function is designed for values of x that are greater than or equal to what? Negative 2. So when I do my sign analysis, I only have one region to check. And since 0 is available, oh my God, this is beautiful. Isn't 0 available? So plug in 0. You guys know something? That second derivative is what? Is it positive? So what does that mean? Is that 3x plus a? Do I do my arithmetic okay? Anybody find any errors? That's what it means. It looks like it's what? So here's our conclusion, right? F is concave up on what interval, ladies and gentlemen? From what? -2 up to infinity. Why is it open intervals? This is the second derivative. At -2, the derivative does not exist. So it's not positive. Does that make sense? So here's your concave up interval. Is it concave down? Mm-mm. Okay. Okay. So it's x over square root 2 plus x. So you say, well, what does Desmos say about all this? Y equals x square root 2 plus x. And let's change that. X is -2. Okay, maybe something like that. And I'll change the y value. Okay, so here's what I'm going to do. Is it true that this curve is concave up from -2 to infinity? You guys see my point? So what they're saying is this thing holds what? Holds water. You're holding water, concave up. Easy peasy lemon wet. So I think you assume students could do derivatives. You assume they could do sign analysis. You guys know what I'm saying? So this is kind of where we're at. We're doing concavity now. Let's see here. I think one of these questions, they're all interesting. See, we already did all that other information here. There's that curve. Should we dare try this one? Should we try that one? What do you guys think? What time do we have? Huh? I don't know. How about this? Oh my God, I'm feeling so what? I hope I had enough coffee in me. Go, whoa. Let's go back. What was that derivative? Because I took that question from another book, ladies and gentlemen. And that other book had people get the second derivative. So maybe we only have time to get the second derivative. What do you think? Okay. You might say, what would I do? I think personally, you know what I would do? I'm going to pull out the negative sign. I'm going to do the derivative here. You guys okay with that? 4x plus 2 minus 2x squared plus 2x plus 1. I'm not going to do the derivative with this one, though. X squared, x plus 1 squared, okay? And let me try to make it so you can at least see this. X squared, x plus 1 squared, okay? So I'm going to do a note here, by the way. I want to find out what that derivative is by product rule. Okay, you guys see what I'm saying here? Let me put this in red. Product rule. So x squared derivative of x plus 1 squared plus x plus 1 squared derivative of what? X squared. Don't forget chain rule, okay? So that's going to be 2x squared x plus 1 plus 2x x plus 1 squared. Let me double check it all. And maybe here, I'm going to say this is what? X to the 4th, x plus 1 to the 4th. Oops. 4th. Okay. Can I factor that 2x squared plus 2x plus 1? I don't think it's factorable. Is that right? It's not factorable. Is that right? That's correct? Or is it factorable? No, no, 2x squared over, I'm talking this. From my memory, this was not factorable here. Because a lot of times the algebra, this is factorable. Here, this is 2. 2x plus 1 is factorable right in here. So I think the fact that that's not factorable is not a good sign. Is this factorable over here, though? Yeah. Let's do that. 2x, x plus 1. You guys watch the video, greatest common factor? Okay. Then this is going to be x now plus what? And just plus an x plus 1. So this would be 2x, x plus 1 times 2x plus 1. Okay, that looks a lot nicer. Let me double check though. 2x, because I'm not awake. Yeah, I think that's okay. All right, 2x, x plus 1, 2x plus 1. I'm going to factor that one. And that is a lot nicer. Okay, let me see if I can write everything down here. So I can get this here. Okay, so we have a negative. I'm going to do it a little smaller. X squared, x plus 1 squared, 2x plus 1. So there's a 2 there. 2x plus 1 here. And then you got minus that ugly polynomial. 2x squared plus 2x plus 1, but I think it'll be okay. And then this is going to be that 2x, x plus 1, 2x plus 1 term over x to the 4th, x plus 1 to the 4th. Okay? Now, here's what I'm going to say you guys want to do. Factor this out again. Maybe make sure where that negative sign is, though. That negative sign is out here. So I want to be careful. So what I'm going to factor out, again, is the greatest common factor here. Got the negative sign. So we're going to factor out, okay, 2x, x plus 1, 2x plus 1. Okay? It's always going to be the smallest power here. And now it looks like we'll have, we factor that out, 2x squared, I want to double check, x plus 1, 2x plus 1. Okay. x plus 1 minus 2x minus this what? 2x squared plus 2x plus 1 over x to the 4th, x plus 1 to the 4th. So this is where you'll do some more algebra right in here. And that portion will be x squared plus x. So distribute here. Minus 2x squared minus 2x minus 1. So I'll get minus 2x, x plus 1, 2x plus 1 times, looks like that's going to be a negative what? Negative x squared minus x minus 1. X to the fourth. X plus 1 to the fourth. I can factor out a negative 1, and then that becomes positive. Okay, so it looks okay now. The only thing that comes out, though, is this x, and this is now third power, right? So the y double prime will be 2x plus 1 squared. Did I make a mistake? Yeah, I did. Okay. Double check. Oh, and then here, this will be the third power. Okay. So 2 now. Negative where? Well, okay, here's what I'm saying here. Here's what I said here, right? Here's what I did, though, to let you guys know. Factor out a negative 1 here, right? So when you factor out the negative 1, x squared plus x plus 1. So this negative 1 times negative 1 is gone, and that's why I had here this term. And so I can actually really easily find now. Now you can do sign analysis a lot easier now. So yeah, I did take care of that negative sign there. I did mention that. I factored out the negative 1, and the negative times the negative is gone. X plus 1, 2x plus 1 times that, and we did some simplification. I can tell you, this is a second derivative. Very easily, the numerator being 0 happens simply when what? X is negative 1/2. You can try to see if the second polynomial gives you a solution. I don't think it's factorable. So you have to look at b squared minus 4ac. So it would be 1 minus. So this is not, this portion here will not give you any. This portion here will not be 0. This cannot be 0. So that looks like it makes sense. Second derivative is undefined or does not exist, right? Depends on how you look at that. Yeah. At x equals 0, let's see, it doesn't even want to write anymore. Okay. Second derivative does not exist, where x equals 0 and x equals negative 1. So your sign analysis, just so you guys know, was the domain restricted in any way? Was it restricted? So negative 1/2, 0 does not exist. Okay, so I'm just going to set it up for you guys there. And you'll have region again 1, region 2, region 3 for your sign analysis. and region 4, sorry. However, it did have a restricted domain. I think we only threw out 0, we threw out -1, so it's not an interval. But that's okay because your derivatives do not exist there. Anyway, so it does all other real numbers work. So you guys can use as test points -2, +2, and maybe negative what? 3/2, and then maybe a positive negative what? 1/4. So all of these will be good for test points for you guys. But again, you're doing sign analysis on this here. On the second derivative, so you might want to punch that in. This is the second derivative here. Do your sign analysis on that and find what happens to those at those values. Yeah.
Isn't it the domain like restricted? So
Well, you only threw out two numbers, 0 and -1. Your original function is what you see up here. So this is not defined at 0. And it's not defined at -1. So those numbers were out to begin with. But that's okay, because at 0 and -1, what's the story with your derivative? Second derivative does not exist. Of course it doesn't. You have vertical asymptotes for the function at 0 and -1. So you have some vertical asymptotes there. So, double check those, do some sign analysis. I can say probably you might want to use your calculator and say -1.5, -0.25. Try that out. And I do have the extra examples where? On my website. Don't I have extra examples for you guys there? So there you guys go. You can have extra examples here for this. So we'll look at some of this stuff again tomorrow. So we'll see you guys later. Take care. Stay safe. Have a wonderful day. I'll put homework, if I haven't already, in Canvas. All right, ladies and gentlemen, let's get back here. Okay. Whew. Okay, so remember the question that we did yesterday, is that right? We didn't finish the sign analysis. I do want to finish sign analysis on that second derivative here. Okay, so I do have it up and running there. Just to be complete here, go back to the original function. Remember, this function has vertical asymptotes at 0 and -1. So you might even say to me, well, how do we know? Well, because you set those denominators equal to 0 and you find that there's vertical asymptotes, right? So this is the vertical asymptotes that we were talking about, if I get that out of the way, yesterday. So that's the issue. So then you might go back, and we did say this as well. We said, okay, all right, ladies and gentlemen, yes, the second derivative. What's the deal there? So this is where we're at. We got to find the signs of this second derivative. So we're going to put test points in. Is that right? And remember, for test points, we only care about the what? The sign. We don't even care about the what? About the answer. You guys with me on that? Now, just looking at this right now, the denominator portion, I can say to you, well, -2, what, to the third power is -8. -2 plus 1 is -1 cubed. Those are negatives. So if I look at the denominator, isn't that going to be a positive answer? Okay, you guys okay with that? And I think this is squared here, so let's look at this. Let's look at this portion here. 2 times negative 2, is that negative 4 plus 3? Isn't that negative? And then negative 2 squared is 4. What's 4 minus 2? 2. 2 plus 1, isn't that positive? So it looks to me, region 1 is what? Negative. Is that true? All right. Now I'm going to do region 4, which means the test point was positive 2. And I don't care about the what. I don't care about the answers, just the sign. So it looks like the denominator is positive, and the numerator is positive, right? So it looks like that's going to be a positive what? Region 4. Okay, now let's do the more difficult versions for the signs. Negative 1.5 here for this test point. Is that right? Negative 1.5, negative 1.5. So we're doing sign analysis. So let's do these signs here. And negative 1.5 cubed. So if I say down here, isn't that negative? Negative 1.5 plus 1 is negative 0.5. Cube that. That's going to be negative. So negative times a negative is a what? Positive. So double check, ladies and gentlemen. And then negative 1.5 here as well with a negative 1.5, negative 1.5. So 2 times negative 1.5, isn't that going to be negative 3? Negative 3 plus 1 is negative 2. So this portion is what? Negative. But what is that negative? What is that? Negative 3 halves squared is going to be 9/4. Is that right? So I'm right here with the arithmetic. So we say positive 9/4. Let's do that. Minus 3 halves plus 1. Isn't 9/4 2.25 minus 1.5 plus 1? So it looks like that's going to be positive. Double check. Is that right? So it looks like a negative times a positive divided by a positive will be what? Negative. So it looks like this is negative. Yeah. What's that? Ah. Thank you. Good job. Let's use then. Oh, thank you. That'll change everything. Good job. All right. So what is this we're going to use here then? What's between negative 1 and negative 0.5? So negative 0.5, negative 1, negative what? 3/4, I guess? Is that good? Double check. Okay, so let's try that test point. Let's try that again. Ooh, negative 3/4. That'll change everything. All right, let's try this again, our arithmetic. So down here, we're going to get a negative. Negative 3/4 plus 1 is 1/4, and cube that, that's positive. So a negative times a positive is negative. Is that right? So double check, ladies and gentlemen. And then 2 times negative 3/4, what's that going to be? It's negative 6/4, which is negative what? Right? Is that negative 3 halves, negative 1.5? So negative 1.5 plus 1 is negative 0.5, so that'll be negative here. So double check. Now we're going to do the more difficult arithmetic. Could you guys put that in your calculator if you wanted, I guess? You guys know what I'm saying? You can put that in your calculator. Negative 3/4 squared will be what? 9/16 minus 3/4 plus 1. So if you wanted, just change these here. Do some arithmetic with fractions, right? So it looks like that's going to be positive. Is that true? Looks positive to me. Okay. So what do we know about that region then? We've got a negative times a positive divided by a negative. What's that going to be? Is that a positive region? It looks like. Okay, now let's try the negative 1/4 here. So double check. All right, negative 1/4. All right, so let's see what these signs become now. So negative 1/4 cubed down here would be what? Negative. Negative 1/4 plus 1 is positive. Cube that, that's positive. So a negative times a positive is negative. And then 2 times negative 1/4, isn't that negative 1/2 plus 1? Positive 1/2, so this is positive. Now all the work over here, which will be what? Negative 1/4 squared is positive 1/16 minus 1/4 plus 1. So again, you could do the arithmetic. 1/16 minus 4/16 plus what? So it looks like that's positive. Is that true? So it's positive. And I'll erase these here. So positive times a positive divided by a negative looks like this will be what? Negative. So double check, ladies and gentlemen. Just double check. So ladies and gentlemen, here we go. Let's get rid of this stuff. And we'll verify this all in decimals, right? But I think, again, the idea for me is that when students do sign analysis, there's always these details of what the answer means. In other words, students need to answer this question, right? So you say, your function is what? Concave up. Where is it concave up? Like, how do you describe your answers? Concave up. Isn't that region 2, region what, 4? Is that true? So we're going to have to describe this. What does this even mean? Region 2 is what? Concave up on intervals -1 to -1/2, union 0 to what? Infinity. Okay, are we reading that correctly? Right, why don't we include those endpoints? Because the second derivative is not positive at those endpoints. Okay, so that's concave up. Now, what's the next one? F is concave down. Where is it concave down, right? So your function's concave down in region 1 and region 3. So what is region 1? What is region 3? What's region 1? Negative infinity up to -1? Is that right? And then 1 to what? Or not 1, that's 0 to infinity. Okay. So double check, ladies and gentlemen, you're able to really read this. Negative infinity up to -1, -1/2. Oh, sorry, -1/2 up to what? 0. We're looking at concave down. Sorry, I got a meeting to think about. So negative infinity up to -1 union -1/2 up to 0. No, you can't switch the order.
Okay.
Okay, it's a good question. This is interval notation. You don't want to write it backwards.
So
It's read smallest to what?
smaller.
Largest.
Okay.
Okay. Now, let me ask you guys this important question because a picture's worth 1,000 words. Are there any inflection points?
Yes.
Where are they? You got to be careful. What's the meaning of an inflection point? It's the point where you change your what? Concavity, is that right? So you say, well, how do you change concavity when you go from what? Smallest to largest, or negative to positive, or positive to negative? Do you have an inflection point at -1? Why not? Because to be an inflection point, again, you got to be a point on the what? Curve. -1 is a vertical asymptote. Similarly, where's the other vertical asymptote? 0. So if you said, oh, I got these inflection points at -1 and 0 because my regions changed concavity, right? Because you look at this and you go, concave down, right? Concave up, concave down, concave up. But then what about at -1/2? Is that an inflection point? How do we know? Is -1/2 on the curve? Say what? Yes. The second derivative is 0, but the point I want to make is your vertical asymptotes are only where? At 0 and -1. -1/2 is a point on the curve. It's in the domain. So the only inflection point you have will be what? At that location, where x is -1/2 and y is f of what? -1/2. So it's important that you not only do the sign analysis, it's important that you know how to read the what? Well, yet you remember the definition of what it is to be an inflection point. Has to be a point on the curve. It's in the domain of the function. If it's not, it can never be an inflection point. And that's where students make their biggest what? Mistakes. Like right here, reading it, thinking of the definition, they spend all that time doing sign analysis, but maybe they don't understand what this even means. And then that's the problem. So this is where it is. Yes?
For the, like, for the, does not exist and versus, and does not exist, it really depends on our, like, domain, right?
I don't know your question.
Like, for the critical
I would say to keep it simple, it depends on your definition. If your definition tells you what the answer is, that's why it's a definition. So you might say, well, what does that even mean? Why don't I focus on something else other than the definition? Because by doing that, you're going off the target. So remember, you got to have a point on the curve to be an inflection point. If it's not, can't be an inflection point. So if those other locations confuse you, it goes back again to the definition. What does it mean? You got to be a point in the what? Domain. It has to. So a lot of times students don't want to even think of what the domain is. See what I mean? This is something that is an important thing. People don't care about the domain. They go, I don't care about the domain. And then they run into a lot of trouble and they don't know how to answer the question, you know. So I think that's kind of the big deal for me. And then, I mean, hopefully we did everything right. You go, what do you mean? Let's go to Desmos, right? Does Desmos even have? Yeah, we do still have that, right? If I get rid of this. And if we can, it does look pretty good. It looks like we're correct. I think let me do a little bit more though. Let me do x is 0 and x is was it -1? Yeah. Okay, there we go. There we go. Let's bring this picture in. Add to the existing note called what? Concavity. Okay, so double check. Remember this concave down from -infinity to -1. This is where your asymptote is. So if I can maybe, I don't know, get a highlighter. Right? This is where -1 is. Isn't it concave down? Does not hold water? That's not concave down? Concave up. Here's the inflection point. So does that hold water? Concave up. And then you don't hold water. Concave down, and then you hold water. So I can even label that just in the picture, concave down, if I can get this. Concave down, concave up, concave down, concave up, inflection point. It's a point on the what? Curve. These vertical asymptotes are not on the curve. This is why you can't say it's an inflection point. It's not a point on the curve where you change concavity. So it looks like we were good. It looks like our analysis was what? Right on. And that's what they call this analysis, by the way. So there you guys go. And I think I'm going to go back to, what did I want to do? There's a lot of different options. I mean, this is a good one too. Do you guys remember this one? You got this derivative, number 4. We got some trig, or do we want to go back to the others, right? Maybe you don't want to go there. Let's go back to the original that we worked on. Intervals of increasing, decreasing, yeah. So we'll go back to the originals. That's the curve we just talked about. Oh, what about this one? Should we try this one here? Woo! You say, Mr. Judge, a trig? I skip that. That's a popular thing to skip. Ooh, let's try this one. You guys want to try this one? Do we do this one? We didn't even bring the curve in. Okay, let's do this. Let's go back, okay? This is the original curve. Y equals sine minus 2 cosine, restricted domain 0 to 2 pi, and then y prime is cosine plus 2 sine. You want to try that one? Let's try that one. But I'm going to need to bring this in. Copy. So let's go back to concavity. Okay, so now we're going to do a sign analysis on the second derivative, right? What do you guys know about this here, by the way, since you're thinking domain? Sines and cosines are nice continuous functions. They're continuous everywhere, even in particular, continuous over the restricted domain. Maybe that has meaning for us. Is that right? So that's why you care about that continuity. Okay. Second derivative. What's that going to be? Cosine plus 2 what? Sine. Okay. Do you guys know how to do derivatives yet? Do you guys know what I mean? I'm going to do something. What's the derivative of cosine? Okay, what's the derivative of 2 sine? 2 cosine. Good, that's what I mean. All right, sine, and now this is the second derivative, so we want to get that second derivative, right? Now we set that equal to 0, right? This is not a rational function, so since it's not a rational function, and it's not like a function where you have secants, cosecants, or tangents, there's not going to be locations where it's not what? Differentiable. Sines and cosines are differentiable where? Everywhere. So those are all the little details that you go back and you talk about have meaning, right? So now you say, okay, let's set this equal to 0. Minus sine plus 2 what? Cosine is 0. And then you have what? 2 cosine is what? Sine. Okay, and you got a nice trig equation, and this means that sine over cosine, divide both sides by cosine, right? Sine over cosine is 2, which means tangent is what? 2. All right, so what is the value of x? Now, this is kind of easy peasy lemon squeezy in some ways. All right. Yep. Anyway, so I'm actually showing some of those students in trig the idea of using their what? Calculator. Huh? You go, what? There's an inverse tangent curve? Yeah, look at that. This is what I talk about trig. Anyway. Second inverse, oh, that's not inverse tangent. Can't see. Second inverse tangent, there we go, of 2. Now, I just want to let you guys know, my calculator is set to degree mode. You might say, how do you know? Well, I could double check. It's in degrees. I'm gonna convert it in a minute. They didn't give us any sort of instructions on this, did they? Right. So this is 63.4 degrees. I'm just gonna say this angle is approximately what? 63 degrees. You guys with me on that? However, what's the domain of the function? Oh, I went too far. Our function's domain is from 0 to 2 pi. Is that right? All right. We're going to have to bring in some trig information. I apologize. Okay. Anybody remember anything about inverse tangent? What's inverse tangent defined for? That's a detail. Isn't that defined for what? Negative pi over 2 to what? Positive pi over 2. In order to have an inverse tangent, you had to restrict the domain. You had to make tangent 1 to 1. Is that right? So that's important because that means you threw out quadrants what? 2 and quadrants 3. Inverse tangent's only good for what? Quadrant 1 and quadrant what? 4. You guys okay with that? So I want to just remark about this. Okay. However, you said that's good to know. However, from 0 to 2 pi, how do we use that information? Where is tangent positive? Because the domain is 0 to 2 pi. So this is how you use that. Even though you remember you restricted the domain to get inverse tangent, the first angle, tangent's positive in quadrant what? 1. So we already got that 63 degrees here. Where is the second angle? Because this is not restricted. This is 0 to 2. It is restricted, but it's a different restriction. It's over the whole unit circle. So where is the second tangent angle going to be? Quadrant what? Anybody want to tell me for all students take calculus? Where's the second one? Isn't it in quadrant 3? You say, how do we know? Because what's the meaning behind all students take calculus? Yeah, quadrant 1, quadrant 3, tangent's positive. What's the relationship between that 63 degrees and the quadrant 3 angle? You have to add what? 180 degrees? So here's your two solutions. X is 63 degrees, and X is what? 180 degrees. Oh, sorry. 240 what? 243. So you have the two solutions. Okay, 243, because it's 180 plus 63. Those are the two solutions. However, what are these in terms of radians? Right, pi over 180, is that right? Pi over 180, you convert those. So your two solutions are going to be now what? Go to your calculator. So this is the kind of question that wasn't really nice because they let you use your calculator, so that was nice, but it wasn't a nice special triangle solution. So take that 63 times what? Pi divided by what? 180. That's about 1.10. Let's go to the nearest tenths. Or actually, I'd like go into the, let's go to the nearest hundredths, thousandths. 1.10 hundredths. Convert the other angle, 243, times what? Second pi divided by 180. So in this example, 4.24. They didn't give you nice special angle solutions. They gave you numerical solutions, and that's okay. In some ways, that's easier. You just have to convert these to radians because your sine analysis is from 0 to what? What is it from? 0 to what? 2 pi, and 2 pi is approximately 6 point something, right? You say, how do we know? Because that was the original function. 0 to what? 2 pi. So, all right, the second derivative now, 1.100, 4.24, you have a 0 for that second derivative, right? Your second derivative is, what was that second derivative? Negative sine plus 2 cosine. Okay, so this is where the second derivative equals 0 here. So that gives you, 1, 2, 3 regions again. 1, 2, 3 regions. Get your test point. So maybe 1 is a nice test point. Oh, thankfully. And then maybe, I don't know, 2 or 3. 2 is a test point. And then maybe 5 is a test point. You guys okay with that? So what I'm going to do something here is an extremely important detail. Because the devil's in the details. How would you guys test these regions? Right? How do you guys test these regions? And what are all of those numbers that you guys see there? Are they degrees or are they radians? Ooh, degrees or radians, because that's going to be a big deal. That's an issue. What are those numbers, radians or degrees? Be careful. When we converted, these are now what? So what are radians? Do you guys know what a radian is? I harp on this in my trig class over and over again. Radians are real numbers. Go, real numbers? Yes, you can't even do calculus without real numbers because that limit stuff. Anyway, so what that means is when you go to your calculator, be sure to do what now? Change the mode. That's my point to you. Go to the mode, and now you got to change the mode to what? Radians. Yes, every gory detail. What's the second derivative? Negative sine plus 2 cosine. What's our first test point? 1. All right, let's try that. So here's what I would do. I'm going to go negative sine. Oh, I have to help to hit the calculator. Negative sine of 1. Okay. Plus 2 cosine of what? 1. I don't care about the answer. What do I care about? Yep. Region 1 is what? Positive. All right. You guys see how easy that was? All right. Let's see about region 2. What's region 2? We're going to say negative sine. What's the test point? 2. Good. Close that. Plus 2 cosine of 2. And up. What do you guys get? Negative. I don't care about the answer. I only care about the sign here. Okay. Now region 3. What's your test point? 5. Negative sine of what? 5 plus 2 cosine of 5. And you get what now? It's positive. And now a picture's worth 1,000 words again. So, okay. Region 1. What do you guys know about region 1? It's positive. That means it's concave what? Up. Region 3. Concave what? Up. Rich region 2. Region 2 is concave down. Easy peasy lemon squeezy. So now this is kind of nice because now you can say the curve, it doesn't matter if you call it y or f, but f is concave up on what interval here? This is important, ladies and gentlemen. Concave up on what interval? This is why I go over this detail. Okay, what's the definition of being concave up? Holds water. What else? It's where the second derivative is positive, right? So isn't that from 0 to the radian value 1.100? Why did I write it this way? Why did I include 0? It's positive. It's actually going to be 2 if I plug it in, but the point I'm making is sometimes students don't know the difference between being positive and 0. And that's kind of what's happening here. In other words, you're going to include the 0. You're not going to include here, right? So it's going to be a closed and then an open. And then what about over here? It's going to be a what? Open forever. So to be union 4.24 to infinity. All right, that's what it's going to be. Oops, sorry. Not infinity. Up into what? 2 pi. Do we include 2 pi? Yes. Sorry about that. Looking at my own picture. Thinking about my meeting. You guys have no idea what my meeting's about. Woo! See, I'm thinking about the meeting. I got to talk to, I'm not going to say it. I can't get in trouble. I'll get in trouble. I got to talk to a discipline in a system. I can't say. Oof.
Close the door.
No, the doors are.
Did they listen to your lectures?
Huh?
Did they listen to your lectures?
Who?
Higher ups?
Somewhat, but so they called me for this discussion here. This IGETSI, if you guys know what IGETSI is, there's going to be a new transfer agreement kick in June. That new transfer agreement. I'm on the math area 2, right, of that transfer agreement.
Like you need more pauses to transfer?
Isn't it the articulation?
It's articulation, but it's for UCs and CSUs. So that's one agreement for both. Now there's some CSU faculty are pissed because that agreement changed for their system in some small way that they say make it now harder for their students in terms of math, my standard area too. So I now have to listen to all of that stuff.
It's going to be effective June next year?
Well, it's supposed to be done. Yeah, I believe so. It's supposed to be done. We're supposed to get this stuff done by winter, and it's going to be, I think, starting June. The new IGETSI. It's the new transfer agreement. It's called IGETSI, but it's for both systems, the CSUs and the UCs.
It'll get worse or it'll get better?
I don't. It depends on your perspective, and it depends on.
What is it though?
What is it? I can't tell you. I got to talk about calculus.
Is it gonna be about calculus though? Like
No. No, it's not going to change for that. It's just there's a particular discipline, really two particular degrees that are not happy.
close the door.
I'll tell you maybe one day before this, they're not happy, and oh my God, I have to deal with these emails. And then I have to do so much plan of attack on a night's notice where I have 2 other meetings for other plans of attacks. It's not even a plan of attack. I think of it that way. But it's just created an argument. So that's why I have some of this stuff here that you guys see. And anyway, it's kind of sad if you think about it, but whatever. Won't go into the details. There you go. There it is, ladies and gentlemen. Are there any inflection points? Go back to the what? Definition. They have to be points on the curve where you change concavity. Does that happen anywhere? Sure does. It happens where? Here and where? Here. Is that right? Are those points on the curve? You betcha. Well, there's 2 inflection points in that interval. And you go, wait a minute, is there? Yeah, I'll show you guys. And you say, well, where are they, right? Well, here's what you guys want to write. At 1, 1, 0, 0, and then f of 1, 1, 0, 0. And what's the other one? Is it 4, 2, 4? Yeah. At 4, 2, 4, and then f of what? 4, 2, 4. There it is. So here's our picture. It's worth 1,000 words. And that's how you answer this question. Now, what was the original function? So if I go to Desmos, I might still have that sine minus 2 cosine. Do I have that? Okay, here we go. Y equals sine minus 2 what? Cosine. And the domain was from 0 to what? 2 pi. Because, ladies and gentlemen, that's it's a periodic function. And this is why I restrict the domain. Okay. So I just want to share with you guys. See that? See that? Oh, looks pretty good. Looks pretty good. I'm going to bring that all in. Remember, we did an approximation, so our numbers might be slightly different. Let's bring that into notability concavity. Okay, you guys okay with that? Now let's take a look at what this means here. Okay, notice our answers from 0 to 1.100. This here is what they're talking about. This is where it's concave up. From 0 to that 1.110 we approximated. And this here, right, 4.249, we only get to the tenths. It's an approximation. Concave up here as well. Is that right? So you say, what are you talking about? Holding what? Water. That kind of curve that way. That curve this way, holding water. And yes, in case you guys didn't know, that's where this is about 2 pi. Okay? And then there's 0. And right in here, you're concave what? Down. And there you guys go. So that does look good. And there's the inflection points here and here. It's the location on the curve that you change your concavity from concave up to concave down. So you guys can kind of see all that. And our numbers are slightly off because of our approximations. But ladies and gentlemen, yeah, that's the meaning of this sign analysis on the second derivative. What do you guys think? Call it I for inflection. interesting. Yeah. All right. Anybody have any questions on this? Yes.
Are you gonna give us like a theory for absolute value and everything?
What's that?
Absolute value?
Give you what?
A derivative?
No. Nope. Anyway. Okay. Any other questions? No? Yes.
You know, like how to find the domain for the function? Is there any like equation to use?
No.
So you really depends on like which like specific question it is.
It depends on what kind of function it is. If it's a rational function, your domain's all real numbers except where the denominator is zero. That's where you have vertical asymptotes. If it's a square root function or an even index function, like 4, 6, 8, you set what's under the radical to be greater than or equal to 0. Those are the values. And then you say, well, what are the other functions? Well, you have trig functions. Sines or cosines are nice continuous everywhere functions. The ones that are not continuous everywhere are the reciprocal functions, like secant and cosecant, but also tangent, cotangent. They have, I should say, locations where you have vertical asymptotes. So the answer to the question about how do you get the domain from these, let me also remark, polynomial functions are nice and continuous what? Everywhere. So the domain's all real numbers. So it really goes back to courses you took, like in trig or even in pre-calculus or in intermediate algebra. Because I know in intermediate algebra, I ask domain questions, they do that. And then some of the stuff that we're looking at now, even the continuous functions, they're kind of related to the domain in a lot of ways, right? Very much related. Where they're continuous, it's really where they're defined. So, so a lot of those little details. So to say, is there a simple equation that answers all of those things? The answer is no. There isn't a simple equation that answers all of those questions. It's not one equation. It's just looking at the different settings of the different functions that are out there.
Oh, I see.
So if you guys even remember, if you took, for example, a pre-calculus course, right? Or even college algebra, there's a lot of graphing in those courses, right? You find, for example, intercepts. Like I know my trig class, they're going to have to tell me intercepts of various trig functions. Tell me where the vertical asymptotes are. Tell me where's the maximum or minimum values. All those things for trig functions. They got to do the analysis. And so, all of those are very meaningful things because they come back here. Like if this function originally given to students, they got to be able to read that and say, where's the highest value, where's the lowest value on the curves? So that's exactly what we're doing in calculus. Where's the relative max, relative min? And so you do some of those things in these other classes. We even do what's called horizontal asymptotes. And you might say, what are horizontal asymptotes? Well, in a course like pre-calculus or even college algebra, they sometimes call that end behavior. You guys know what end behavior is? It's behavior at the end of the functions. And that's what we're going to discuss really next, end behavior. So